In this video, we'll take a look at resistivity. Now, before we jump into resistivity, we're going to talk a little bit about resistance, right? Electrical resistance. As we mentioned before, electrical resistance is a measure of the opposition to the flow of electric charge. And since you know that basically the rate of flow of charge is an electric current, then essentially electrical resistance is opposition to the flow of or to an electric current, right? Now, an analogy I like to use basically between resistance and current and is garbage in a drain. Now, if there's a drain and it is free of garbage, and when it rains, there's a clear path for the water to flow, and basically it doesn't back up and there's basically no flooding, the water flows freely. However, if the garbage is full of drain, if the drain is full of garbage, then basically the garbage acts as some form of opposition to the flow of water, and therefore the water doesn't flow as readily as when the drain was free of garbage. So in this analogy, the drain could necessarily be, for instance, some form of conductor which facilitates the flow of the water, and which represents the electric current in this case. And the garbage, of course, represents the resistance. So the lower the resistance, then it means a larger current will actually flow in a particular part of a circuit. As a matter of fact, current is known to flow to the path of least resistance. So if there are two paths in a circuit, one which are of a greater resistance to another path which is of least resistance, then what we'll have is that a larger portion of the current will typically flow to the path of least resistance, right? So again, So having said that, experiments have shown that the resistance of a conductor is proportional to its length. So resistance R is proportional or directly proportional to its length L. Experiments have also shown that the resistance of a conductor is inversely proportional to its cross-sectional area A. So the resistance is directly proportional to its length. What does that mean? It basically means that if nothing else changes and we change the length of the conductor, the resistance will change. But how? The longer the conductor, the greater the resistance. So because that direct proportionality relationship, if you were to double the length of the conductor without changing anything else, the resistance will be doubled. If you were to triple the length of the conductor without changing anything else, the resistance would be tripled. If you were to quadruple the length of the conductor without changing anything else, the resistance will be quadrupled, and so on. All right? So generally, provided everything else remain constant or unchanged, the resistance of a conductor will increase with length. Let's talk about this relationship. The resistance is inversely or indirectly proportional to the cross-sectional area. What exactly does this mean? It means that the bigger the area of cross-section of the wire, then the smaller the resistance, right? So generally, thicker wires tend to have smaller resistance than thinner wires due to the fact that thicker wires will have a greater cross-sectional area. So what is the effect of changing the area if nothing else is changed? If nothing else is changed and we double the area, then this results in the resistance being halved, because it is an inverse proportionality relationship or an indirect proportionality relationship, or right? If we were to quadruple the area of cross-section of the conductor, then it would mean that the resistance will now be a quarter of its initial value, right? So that is the effect of the length and the cross-sectional area independently on the resistance of a conductor. But of course, in many cases, both length and area could change simultaneously, and we'll then have to consider the effect of each on the resistance, right? Now, if we were to combine these two relationships, what we'll get is this, that R is proportional to L over A. Good? So because the resistance is directly proportional to the length L and inversely proportional to the cross-sectional area A, when we combine them, we get that R is proportional to L over A. Now, whenever we have a proportionality symbol, we can actually replace it with an equal sign and introduce a multiplying constant. So we can write R equals L over A. Now, what is the multiplying constant that we'll actually introduce to this equation? It is a Greek symbol called rho kind of resembles a P, but with more of a hunch, right? So this Greek letter is called rho, spelled R-H-O, and in this case, it is used to represent resistivity. So rho represents the resistivity of the material, right? We can actually transpose to make rho the subject, and so we can get the resistivity in terms of the resistance, the length, and the area. So doing that, we have R is equal to rho L over A. Multiply both sides by A, we get RA is equal to rho L. Then we divide both sides by L. The L's cancel, and so we get rho is equal to RA over L. Right? So this formula basically gives the resistivity in terms of the resistance, the cross-sectional area, and the length. Right? Now, let's look at a special case. What happens if L is equal to 1? If L is equal to 1 meter, and say A is equal to 1 meter squared. If L is equal to 1 and A is equal to 1, then essentially what we get is that the resistivity is equal to the resistance. And it is this relationship which is actually used to define resistivity. Right? Now, before we define resistivity, you must bear in mind that resistance is a property of a component or a device, like a piece of wire, it could be a lamp, right? So resistance is a property of a component or a device, whereas resistivity is a property of a particular material. So whereas you can speak about the resistance of a particular length of wire or a particular conductor, you would speak about the resistivity of the material from which the conductor or the resistor is made. So from this relationship, we can see that the resistivity of a material is numerically equal to the resistance of a piece of that material of length 1 meter and cross-sectional area 1 meter squared. So the resistivity of a material is numerically equal to the resistance of a piece of that material of length 1 meter and cross-sectional area A. And typically, for any piece of material to have length 1 meter and cross-sectional area A, it typically must be a cube, right? So essentially, we can say that the resistivity of a material is numerically equal to the resistance of a cube of the material of sides 1 meter in length. All right? So basically, if we have a cube of any given material of sides 1 meter then the resistance of that piece of material will be numerically equal to the resistivity of the particular material from which it is made. All right? So in this video, we gave a recap of resistance, and of course we also touched on resistivity, and we showed how resistance varies with the length of a conductor, how it varies with the cross-sectional area. We combine them and we're able to get an equation including resistivity from which you actually made resistivity to the subject, and we applied certain special conditions. When the length is equal to 1 meter, cross-sectional area equals 1 meter squared, we say that rho, representing resistivity, is equal to R, the resistance, and we use this relationship to formulate a definition for resistivity. And we basically said that the resistivity of a material is numerically equal to the resistance of a piece of the material of length 1 meter and cross-sectional area 1 meter squared. And again, for a piece of material to have a length of 1 meter and cross-sectional area 1 meter squared, it means it can only exist in one shape, which is that of a cube. So having said that, we can say that the resistivity of a material is numerically equal to the resistance of a cube of the material of sides 1 meter in length.